Welcome. We have introduced the idea of uncertainty of random variables. We have introduced the idea of reduction in uncertainty of a random variable by knowing another random variable, which is also called mutual information. So, we have extended that idea to call to in the case of continuous random variables by using differential entropy as a measure of quantifying the dependence between two random variables, that is the difference in differential entropy of a random variable x and the differential entropy of a random variable x given another random variable y, in our case stimulus and response. So, using this mutual information, we can now quantify how much dependence there is between a random variable with another random variable, although we cannot explicitly model the relationship between the stimulus and response or two random variables x and y. So, we cannot have a predictive model per se directly using mutual information, but we can quantify how much dependence there is, so that we can test models by knowing that okay, the dependence can be up to this much. So, does the model capture that much dependence? So, in that way we can get an idea of how much our model works or how well the model works in the ideal sense, because that is or if there is more room for improvement. Also, we will later on talk about how we can take the help of mutual information in order to identify the possible features that a neuron encodes without directly being able to model it, but empirically deriving a possible model from the data. Another way of quantifying mutual information is through Kullback-Leibler divergence or Kullback-Leibler distance, that is Kullback-Leibler distance. It is also called relative entropy. We simply write it as d of kl between two distributions p and q. Let us say p is a distribution of a particular random variable x, and q is another description of the distribution of p of the same random variable. I mean, basically the two distributions are defined on the same support, that is the possible values taken by x. What dkl pq provides is how different, or quantifies how different the two distributions p and q are, or how far away one distribution is from the other in different kind of space. Here it is not truly a distance measure, because it doesn't follow symmetry, it doesn't follow triangle inequality. However, it in some sense quantifies the difference between the two. That is applicable in terms of communication in source coding. Basically shows the amount of, or the extra amount of loss incurred by making a mistake in encoding a distribution p by another distribution q, or representing one distribution p by a distribution q. So, there is a physical meaning associated with it, which is more applicable to communication systems or source coding. Here, however, we can use this for a variety of purposes, where we can quantify the distance or the difference between two distributions without making any assumptions about the possible distributions or the underlying distribution. So that is given empirically or observed P and observed Q, if we can quantify DKL of the two distributions, we can quantify how different they are and make conclusions based on that. So this does not require us to assume that okay, P must be uniform, Q must be uniform or Gaussian, as we will be doing in many other cases in computational neuroscience. We will see that later on. So this allows us assumption-free way of quantifying differences between two distributions. So, but in another way that this DKL is important to us is that this also provides a way of defining mutual information between two random variables x and y. So, what is the definition of DKLPQ? It is simply that it is summation P of x, and x is sum over all possible x's, that is the support of the two distributions, log of Px by Qx. So, as you can see, this is not symmetric, and so it is not truly a distance, although we will call it KL distance. So this definition of KL distance appears in the definition of IXY also. That is, we have IXY equals, we have said that it is h of x minus h of x given y. So by our definitions of h of x and h of x given y, we can show that it is also given in your handout that this is equal to basically sum over either all the x's and all the y's, p of xy, this is the joint distribution of p of x and y, log of p of x and y divided by p of x and p of y. Now, if you look at this, this is a very similar expression as KL distance. So, in this case, we are looking at two distributions. Now, this let us what was p of x before is nothing but the joint distribution px comma y, and what was q of x before is nothing but the product of the marginals p of x and p of y. So this mutual information then turns out to be the DKL of the joint distribution px comma y and the product of the marginals px into py. So now in the interesting way of looking at mutual information is how different is the joint distribution from the product of the marginals px and py. So remember that when two random variables x and y are independent, then the joint distribution pxy is the same as the product of the marginals px into py. And in that case, when x and y are independent, as we expect, the mutual information IXY in that case is 0. And the more different the joint distribution is from the product of the marginals, that is the mutual information keeps on increasing. In other words, the mutual information is the distance between the joint distribution and what the joint distribution would have been had the two random variables been independent of each other. So, had they been independent of each other, then the joint distribution Pxy should have been Px times Py. However, the observed joint distribution Px comma y is whatever we are looking at, and so the distance between them, or the KL distance between them, is the quantification of dependence between x and y, that is the distance from independence. So, now if we go back to our idea of stimulus and response, then we have the stimulus and response. All we need in order to compute this mutual information is just one thing, which is the joint distribution of Ps and R. What is Ps and R? Ps comma R is the joint distribution. This is simply the output of experiment where we use different stimuli depending on the question we want to answer and make observations about the response depending on the way we want to define the response measure, and by varying the stimuli and repeating the stimuli multiple number of times, we get an estimate of this joint distribution. So, if, as we discussed in the earlier class, let us say our stimulus takes on values S1 up to Sn, and we observe the responses are as either R1 up to Rm. These are the possible responses that we observe, and the stimuli are S1 up to Sn. Let us write this down in the matrix form here, S1 up to Sn. So, each row here is like this, depicting its stimulus, and we already have the marginals. Let us say we give the stimuli equal number of times or present the stimuli equal number of times. So, it is 1 by n in each case, or maybe it is naturally equally probable. So, these are all 1 by n. So, this here is our marginal probability Ps, that is 1 by n each time. So, now in the experiment, what are we doing? We present the stimulus S1, let us say capital K times, and in each of those K times we observe a few times R1, a few times R2, and so on up to Rm. So, based on these values, we get an estimate of probability of response equal to R1 given S equals S1, probability of R equals R2 given S equals S2. Let us say our K is 20 and our R1 is the number of times we observe R1 for stimulus 1 is 2, then this turns out to be 1 by 10. And let us say we observe this R2 0 times, so this becomes 0. Let us say we observed Rm 5 times, then we have probability of R equals Rm given S equals, this is S1, S1 is equal to 1 by 4 and so on. So, we have the probabilities R1, R2 up to Rm given the stimulus is 1, which is this particular row here, and based on what we have 1 by 10 and multiplied by probability of S equals S1, which is 1 by n, which we already have there. This is 0 and this is 1 by 4n. That is, we have now multiplied this by probability of S equals S1 in order to get the joint probability. So this way we can fill up this entire matrix, that is obtain the joint probabilities PS equals SI and R equals RJ. So this is the ijth element in this, so this is the jth, this is the ith, this is the Pij, let us say. So now we have, with the different i's and j's given the experiment, we can fill up this matrix, and we have the, by summing these along the columns, we have the probabilities, marginal probabilities of R, that is P of R. This is R equals R1 up to probability of R equals Rm. So all the components required to compute mutual information is present. That is, we have the joint values, that is sum over, and we have S equals S1 to Sn, or which is, we can write this sum as basically not S1 to Sn, we can write it as I equals 1 to n, which is basically it will sum from S1 to Sn, and this is j equals 1 to m, probability of S equals Si, comma R equals Rj, log of probability of S equals Si, comma R equals Rj, divided by probability of S equals Si and probability of R equals Rj. And by summing them over the all possible combinations of stimulus and responses, we can get mutual information between the stimulus and response. There are a number of issues, practical issues, that will come about when we actually do the computation because of associated bias in measurements in the estimation of entropy and mutual information. So you can see from the KL distance approach that and also the conditional entropy minus conditional entropy approach, that mutual information is greater than 0. That is, it is always it is non-negative. It can be 0 when the two random variables are independent. So they being non-negative, even entropy is also non-negative because the lower limit, the lowest possible uncertainty is 0, and in the axioms also the measures have to be positive in that sense, and you can see that negative logarithm pi log pi will turn out to be also always positive or non-negative, and so because of that, even when there is no dependence, we will get some spurious dependence present from the noise itself, because no matter what, it is always positive. That leads to many issues in the estimation, and so there are ways that if you are going to be actually implementing these, you can take resort to other ways, other means of removing that bias, which is debiasing information theoretic estimates. There are a number of ways that have been used, and we will provide references for those. However, for our purposes, we will take this as one way to compute mutual information, and now we will take this forward in order to see how mutual information and KL distances can be applied in terms of understanding neuronal coding. So if we go into the summary, what we have shown is, if we think of a random variable x, or let us say the stimulus and response, then the connection between them is quantified by this, or dependence between them is quantified by this mutual information of I, S and R, or X and Y. Now, if we think of this circle, or representing the uncertainty in the random variable X or S, and let us say this circle represents the uncertainty in R or Y, let us say, so this circle represents H of S and this circle represents H of R. So the part that is remaining outside of R in S is the uncertainty remaining in S given we know Y. So we know Y, so that means this shaded part is H of S given R. We know R or Y, this is H of S given R. Similarly, we can think of the vertical shaded region here is the region of R, uncertainty of R, that is present if we know S, that is H of S goes to 0, then the vertical shaded region provides us H of R given S, that is the entropy remaining in the response given the stimulus. So the intersecting region, which is the horizontal shaded region, is what we call the mutual information I, S, R, which is nothing but H of S minus H of S given R, or H of R minus H of R given S. So in other words, in this case, the intersection in this Venn diagram form, the intersection is providing us the dependence, or representing the dependence between the two random variables. So another important idea that is required in order to go forward is the idea of the data processing inequality, which simply says that, let us say we have, I will not go into the technical details of this, let us say we have a chain of random variables, that is, from X we get to know Y, from Y we get to know Z, and it is such that if we know Y, then X and Z become independent. That is what we mean by Markov chain here, that is, X and Z are conditionally independent, that is given Y. If we have a situation like this, so let us say we have a stimulus, and let us say from there we have a response. Now, given from the response, we have an estimate of the stimulus, let us say, another random variable S prime, which is something which is also a random variable, and given R, S and S prime are independent because S prime is only dependent on R. The S in S doesn't influence it in any way once we know R. In such a scenario, what we can show, or what has been shown, is that the mutual information between X and Y is greater than equal to the mutual information between X and Z. That is, by processing the response or a random variable to a new random variable Z, we actually lose information. That is, this is what we call the data processing inequality. So what this tells us is that if we use some data to know about a particular random variable, let us say we take R to know about S, and then we process R further to a new random variable, then the amount of information that is going to be there in the new random variable about the first random variable is going to be less than what was there between the previous random variable and the original random variable, that is R and S. So that means there is a lower bound in terms of if let us say we somehow estimate I x z without knowing y, then I x z is a lower bound of I x and y. So this will come up when we look at discrimination based decoding of stimulus and response. So with all these ideas of information theory, we will now later go to applications of them, and we will first consider the case of applying information theory in order to derive possible models between stimulus and response in a particular way. That is what the methodology is, maximally informative dimensions. So remember, we motivated the idea of going into information theory from the fact that we can only model stimulus response relationships only up to a certain degree or order. We definitely can use linear models, which we did using the spike triggered average, which can be extended to higher order models, but obviously there is a limitation as to how far we can go. And so we took the help of information theory, or we said that we will take the help of information theory in order to build or understand what models can be between can be possible between stimulus and response. So given this background of information theory in our two lectures, now in the next lecture we will start off with the applications of the ideas, first with the idea of maximally informative dimensions. Thank you.